surfaces of airless bodies. What happens on the moon? What happens on an asteroid? And what sort of interesting plasma physics we could learn. And just to wake you up, I would like to remind you that there were some glorious days. Oh, wait. Now you are. That's a movie, in principle. Yeah. It's okay, I could show it. I could probably show you that movie. Oh, somebody's birthday, that's good. Oh, shucks. Somewhere there is a media school. Apollo. So, that's the glorious part. By the way, other than being very uplifting, notice how much dirt there is being lofted. In fact, these buggies had a camera, and if you go through the transcript, what ground control and Houston and these guys were talking about, every couple of minutes there is a statement, stop, clear the camera, we can't see where you are going. The other movie I had in mind is somewhat less glorious, nevertheless also points to the fact that it's a really difficult environment to be on the moon and to work on the moon and to do anything. Oh, really? That's interesting. I was playing last night. Okay, my computer forgot, but they have to.
Oh my God!
Yes.
What did you up there? Woo, 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 woo.
Yes.
Okay.
I could just tell you what happens there, and then
go over. Let's make this a little help. Hang on a minute. I'll get there. Keep talking.
All right. So the other movie is less glorious. There's Jack Schmidt tries to pick up something from the ground, and he just.
Is this AVI?
Yeah.
You know what?
Oh yes,
there.
play it right there. Yeah. That's a more seldom viewed set of images. Oh, I'm sorry. Yes. I'm sorry, I misspoke. You're absolutely right. So let's go back to where we need to be. So the question, of course, that it's very exciting to send humans, but is there a piece of physics that we can consider even without astronauts being there? And that is, imagine the moon, here it is. The two graphics pretty much has the same information content. This is from the 70s. This is from NASA today. If nothing else, you certainly learn about the improvements in our graphics capability. Not necessarily there is a whole lot more physics in it. But here is the sun. Certainly this is not to scale. That's the solar wind flow. And of course, ultraviolet radiation is hitting the front side of the lunar surface. UV is actually more important than the collection of electrons and ions. And the sun will generate its own photoelectric sheath. And the surface itself will be positively charged. There is an electric field pointing away. In addition to all that complexity, remember, there are magnetic anomalies that can also do strange things. Then on the backside, there's an interesting physics region. The solar wind, I imagine by now you all know better than I do, is supersonic with respect to the ions and subsonic with respect to the electrons. So the electrons are coming at all times, at all places. They couldn't care less about the 400 kilometers per second bulk flow. Their thermal speed is much higher. As opposed to the ions that represent a nice, well-organized flow, so they will generate a wake. That cannot be maintained for a long time. You cannot have ions going by and electrons keep charging the surface. At some point, the surface charge negative surface charge has to be sufficient in a very naive picture so that an ion that is passing by at 400 kilometers per sec will find its way to keep you equilibrium charging. So half mv squared, if I turn that into potential, you should have kilovolts of negative potential on the night side. That is not really the case. It's much more complicated. The wake fill in and what happens as the plasma flows by is a whole different set of discussions. And of course, we have good measurements and we have collecting more and more data about the details and the counter-streaming streams and all the interesting plasma physics that is behind, actually even behind the spacecraft in the Earth's magnetosphere, or certainly behind the moon and any other object in the flowing solar wind. Now, there are some strange things that relates to dust. These are the first precursor missions that landed on the moon in the late 60s, before humans went there. The surveyor cameras, they were looking at the sun set. They were placed on, these are TV cameras, and when the sun was already behind the horizon, these bright clouds appeared. Whether they appeared at sunset or that was the time that light scattering properties were right, I cannot tell you, but these clouds appeared and people argue ever since, what the heck is this? Some sort of strange glint from the surface, but by the time these images were taken, the solar disk is way behind the horizon. So it's very hard to imagine forward to have surface scattering as opposed to just light scattering on hovering dust clouds. Another piece of controversial measurements is now, this is Apollo 17. The LEAM Lunar Ejector and Meteorite experiment was put on the surface to measure the high-speed incoming flux of interplanetary dust particles. And every time the sunrise and the sunset came by, the terminator passed by or swept over the ground station, the flux of particles that the instrument was reporting went up many hundredfold. So there is something strange going on, and the question is, can you move dust around the surface? And of course, we have these little sketches from the astronauts that stayed in the common module. The spacecraft is approaching the local sunrise, and before you get into the spacecraft itself gets into the sunlight, it sees dust. Most of the dust, or brightness, this is scattered light. Most of it actually, this nice shape has to do with zodiacal dust. Dust between us and the sun. There's a whole lot of dust, and they are forward scattering very efficiently, and you are coming and started to look towards the sun. You see the forward scattered light, and this is about 6 minutes before the terminator crossing. At 5 minutes, something strange happens. Seems that the brightness at a scale height of tens of kilometers appears to follow the lunar surface, and that makes no sense. Zodiacal light, or the dust that is distributed in the solar system, has nothing to do with the lunar surface. So maybe that's a contribution from lofty lunar dust particles. And of course, in addition to all that, they draw these strange streamers, and that's a drawback of technology because probably in your classrooms you're no longer using chalk. But there was a beautiful demonstration with the projector and the chalk when I made a whole bunch of dust. And if you were at the right place at the right time, you see it very bright. And if you were at a different location, you have seen nothing. That can happen to you one lazy Sunday morning when you look towards the window and says, gee, I'm really breathing in all that stuff. And then you turn around and says, oh, it's okay. So let's look at the pieces of physics that goes into it. Of course, we know about solar cycles, and people told us that, don't worry, the sun is only changing a little bit as far as the total energy is coming, but in UV, in short wavelengths, that change is actually quite large. So this is time versus the Lyman alpha intensity as a function of time, and it goes up and down, and that's interesting because I can calculate making a convolution, making an integral of the incoming radiation, the wavelengths of the incoming radiation, and the photoelectric yield that we measured of the lunar dust, and I tell you how much current you produce as if integrating up to a certain energy in the solar spectra. And of course, the moment you you have significant Lyman alpha contribution, you are starting to generate a whole lot of photoelectron current from the surface. At solar minimum and solar maximum and solar flare, that could change between 5 microamps per square meter up to 40 microamps per square meter. This is how much photoelectrons you are producing just to UV. Actually, we have done experiments in the lab where we try to replace the sun with a, now it's a fancier than our first set of experiments, UV light source. We shine on the surface, and we try to tell you the surface properties make a difference. This is cerium oxide with a low work function. It has a high photoelectron yield. You could buy it as a surface or a plate. You could also buy it as dirt, and then you could measure the, this is an IV curve of a long-bore probe, current versus bias potential. And the only difference I would like to show you, these are just the experimental settings, but the dotted lines and the curved lines are solid versus powder. So the surface properties are making a huge difference. This is the saturation current, which is proportional to the electron density that you will find above the surface. Powders generate fewer electrons, photoelectrons, than surfaces do. But you could characterize these surfaces. You could characterize the plasma itself. And then you could do, back to the plasma chamber, a kind of an interesting experiment. Imagine that there is still the dust dropper, and there is the Faraday cup as before. This UV light as before, but this time I am shining onto a photocathode, typically a cesium or something that has a high photoelectron yield. And the setup is such that I can take this plate and push it back and forth. So the dust particle either falls very close to the plate or far away from the plate. I can also measure putting Langmuir probes at various distances. I can measure the electron density above the plate. And it behaves like an exosphere. The photoelectrons are jumping off and falling back because they leave behind a positive charge. And there is a continuously present cloud of electrons, and the density of that cloud is dropping with distance. So let's start dropping dust particles. And I can drop dust particles close, or I can drop dust particles that are far away from the photoemitting plate. And this is the charge that we measured. These are, again, probably 50, 60 micron sized dust particles. These are the charge in tens of thousands of electron units. This is distance from the photoemitting plate. If you are flying very close to the plate, the sea of electrons that is coming from the plate itself is more important than the electrons you yourself are emitting. Your charge will be negative. There is an overabundance of negative charge carriers, or overabundance of electrons right above the plate. If you move far away from the plate, you are emitting your own photoelectrons, and then you are charging positively. Anyone has a guess why we didn't make measurements for zero charge? You can't measure zero charge in a Faraday cup. Anyway, but clearly there is kind of a continuous transition from negatively charged to positively charged particles. So imagine this experiment, and I will turn it 90 degrees. So this is it. Again, in the plasma, there is a pizza tray that we bought at McGuckin. We put dust in it. This time, actually, we do it in a real plasma, so it will be negatively charged. There will be a sea of ions above it. And let's see what happens. If the surface is negatively charged, and I lift off a particle, and I move it far enough away so that its charge is changing to the same charge as the surface itself. If you are very close, you have the opposite charge, because you are swimming in the sea of charge carriers that are missing from the plate. If the plate is negatively charged, there is an overabundance of ions that is diminishing in density. And if you go far enough, then you have the same charge as the plate itself. If you have the appropriate electric field, you could beat gravity. And you could dance and balance the forces and dance roughly above a Debye sheath above the surface. And that's a movie, whether it plays or not. Oh, it will play. That's a movie of I think these were, again, 50 micron dust particles dancing in a plasma. Yeah, the upward pointing electric field multiplied by the charge on the grain would balance gravity. Notice, you cannot dance close, because if you were to dance closer to the plate, your charge would switch and you immediately fall down. So you have to ride above the sheath, roughly about the Debye lengths away from the sheath. So maybe or maybe not, that has to do with these clouds that are hovering about the lunar surface. The statement was that they are roughly about half a meter above the surface, and you know, that is more or less compatible with what I expect to be the Debye length on the lunar surface at sunset. So maybe that's how it works. Another interesting piece of observation is the swirls. These are albedo markings. They happen every once in a while on the lunar surface. And typically, they have to do with magnetic anomalies. The moon doesn't have a global magnetic field. At patches, it has crustal magnetization. So one can argue that maybe it has to do with the excess of the solar wind and space weathering, how electrons and ions come in at different rates because they follow different paths as they hit a region with a magnetic field. So we can do that experiment. Imagine that we're going to buy a kitchen magnet, which is certainly much, much stronger than the magnetic field on the moon. It's 100 Gauss. Anyway, it's kilogauss you could buy. And then put it in the plasma chamber and see what happens. And that's an interesting piece of plasma. And usually we don't discuss that either in fusion research or any other sheath physics, because the type of setups that you could do is such that the electrons become magnetized. So they will be very sensitive where the magnetic fields are, and they will spiral along the magnetic field lines. But the gyre radius of the ions is much larger than the characteristic spatial scales of the magnetic field, and they just come down. They just rain down to the surface. So unmagnetized ions and magnetized electrons are hitting the surface, and then you could make a surface plot. You could take an emissive probe and measure up the potential distribution, and this is where the magnet was buried. And you see this incredibly complicated nonlinear potential distribution. And every time you see big color changes, that's a large electric field. If that electric field combined with a charge on a dust particle, maybe possibly large enough to push particles around and give you these strange markings, strange albedo markings. But the physics is interesting. What happens in kind of an intermediate magnetization region? By the way, you don't even need magnetic fields to get things that are not obvious. All I ask our students to do, to run peak codes to tell me what happens as the sun is shining at different angles if you have a small crater. This is the topography. The sun is overhead, and this is the photoelectric sheath. The electron density, the potential distribution is such that the surface itself is positively charged, and then the potential drops away. There is an upward pointing electric field. You could look at from above, or wait a little. And now the sun is at 45 degrees. It's shining, and of course it's not shining at the surface that is in the shadow, and you immediately generate electric fields. So one can then argue what happens when there is a spacecraft. So we put now a spacecraft next to the crater, and we went through the same sort of issues. What happens with the spacecraft? And this exercise was there to show you that in a dilute plasma, if you make measurements on a spacecraft, it's going to be really hard to understand what you're measuring because it will make a huge disturbance on the environment. Hinz or colleagues try to build big booms and go far away from the spacecraft, but there are issues, and these are difficult measurements, certainly on the surface of the moon, where the plasma density is kind of low. So imagine that we're going to launch dust particles, one at a time. I know the plasma densities as a function of the local where the sun is. I keep launching particles. Some of them will fall down. Some of them will kind of levitate above this sheath that we discussed. Eventually will fall down, and I can keep doing that. And what we notice is that if you start with a uniform distribution of dust particles, if you wait long enough, they will settle into the shadow, into the crater. So the bottom of the crater seems like an attractor for small dust particles. It says, oh, that's unrealistic. Why would you start with a uniform dust distribution to begin with? It's all a matter of your initial setup. So we put all the dirt on one side and waited. That's the blue intermediate. And then we waited, and most of the dust ended up at the bottom of the craters. And then you say, that's odd. Would anyone expect that? And of course, it turns out to be yes. Our colleagues Josh Caldwell and others pointed out that these dust ponds are very smooth bottom surface craters that maybe has to do with dust particles to be filled in. Even on the surface of the moon, when you look at the top close to the pores, there are regions that are permanently shadowed. People argued, that's where we should go. There's a bunch of ice. It's going to be the place to live. And if there's a bunch of ice, if you look at in ultraviolet radiation, and actually this is ultraviolet light, not from the sun, but the background ultraviolet radiation that exists everywhere, you would expect these to be bright because the ice would be smooth and the backscattering would be very favorable, unless it's covered up in dirt. And this is actually the North Pole. And these are little regions that should be bright, but they are dark, maybe because all the little dirt particles covered up the bottom of these craters. There it is, nice, smooth dust ponds on Eros, where a spacecraft landed in 2002 or so. All right, so I have two more of these subjects. One is dusty plasmas in comets, or charging effect in comets. Let's move on. Of course, when a comet is far away from the sun, it does nothing. It's just a big airless object, and all the discussions that we had would be valid. I can make dust moving around. I can do all kinds of things. I don't want to do that again. But of course, there is something interesting when the comet becomes active and its interaction with the solar wind as a function of heliocentric distance changes dramatically from an exposed object that the solar wind and UV directly have access to the surface, like the moon, like Mercury, like asteroids, to an object that is strongly outgassing, carrying dust with it, and makes kind of an interesting region of the incoming flow of the solar wind plasma and the outcoming neutrals that are ionized and make cometary plasma, and the separation between those. So let's start the simplest. Imagine that I would launch a particle from the nucleus, and the only forces I would consider is gravity and radiation pressure. So particle would start towards the sun. The radiation pressure is pushing it the other way. It will nicely come around and turn around. And you could figure out where, as a function of grain radius, where you would turn around depending on your light scattering properties. The quantity that would tell me really the behavior is the beta factor, which is radiation pressure over gravity. And the only interesting part of that is your light scattering, the effective light scattering cross-section, and your density. And typically what I expect, small grains would have very tight umbrellas, big grains would have large umbrellas. So if you would fly across behind the nucleus, you would encounter big particles, and then smaller and smaller and smaller, and then bigger and bigger as you go on the other side. Well, there are often strange things. Comets are not necessarily preserving the symmetry towards the sun. This is actually a drawing from 1858. And you see this strange set of parabolas that are not symmetric with respect to the sun. And you know, maybe it has to do with charged dust. Maybe it has to do with the V cross B forces and the electric field that I feel in the passing by solar wind, the polarized electric field, that is pushing particles in some strange direction. So you could again compare the electrostatic acceleration over the gravitational acceleration, and you notice that yes, you can make these parabolas in pointing in odd directions. You could make it even more complicated. Imagine that I would release a particle, and depending on the plasma environment, I can follow its trajectory. Exactly the same code, or very similar kind of a numerical approach that we have done for the dust at Jupiter or for the dust at Saturn. You tell me the environment, and I, not self-consistently, but just following test particles, I tell you where the dust will go. And then you could do strange things. For example, this is 10,000 kilometers behind the nucleus. That was the case. Jacobini-Zinner, 1985, when the US decided not to send the spacecraft to Heli, but we still wanted to be the first to have a comet mission. One of the IC satellites were redirected to fly through the comet tail. And it's kind of an interesting thing that really, because of the electrostatic forces that we discussed, the encounter was very asymmetric. And we have seen small particles pushed on one side. This is a computer simulation, and I lost the data somewhere. But the little particles are extending way. This is the plane of the motion of the comet. And they were pushed on one side, and the smaller the particle, the bigger this effect, that charging would make you asymmetric. If you turn off charging, everything remains symmetric. Now there is another interesting set of observations. Comet, once in a while, show tails, plasma tails that decouple from the comet itself, or show this wavy structure in the dust tail itself. And that was perhaps one of the clues that told you about current sheets and the directionality of the magnetic field, and what happens if you are flying through a region where the orientation, the azimuthal magnetic field is changing direction. Then everything, the forces are changing sign. So particles that were pushed above the orbital plane of the planet, of the comet, now are pushed below. And you could see this kinematic wave propagating down the tail, which is actually not really a wave. It is just the effect of passing through a current sheet. So comets at high latitudes, either above or below the ecliptic plane, would never show this structure. The closer you are, the more likely that you will cross the current sheet and your tail would show some sort of a dust wave. There was something else. At least it appeared that at Comet Heli encounter, these are the Russian measurements, particles come in bursts. All of a sudden, there's a whole lot of dust, and there is nothing, and there's a whole lot of dust, and nothing else. And the possible explanation for this sort of behavior is the electrostatic breakup of particles. If you go into the solar wind, where the densities and temperatures are higher than in the cometary plasma region, your charges go up, and you could calculate what sort of a tensile strength you need to carry enough charge. If you have charges, the charges repel one another on the grain, you could overcome the tensile strength of the particle, and you blow up. So maybe these bursts of particles have to do with bursting particles as they leave the comet vicinity and get into the solar wind. There is something else that could be very interesting looking ahead of Rosetta. This is, of course, a Cassini discovery of the South Polar region of Enceladus, where we have these streams of plasma coming, neutrals and dust and plasma coming out from the cracks on Enceladus. And when the spacecraft flew through, the Longmoor probe, people were very excited, reporting non-neutral plasma. The electron density was far less than the ion density. Something crazy is going on. So there was this huge release of discovery of dusty plasmas in space the first time. And then we had to point out that these sort of things were seen decades before in the Earth's ionosphere, when you see radar scatter, and that would tell you the electron density profiles. In the regions where most incoming meteorites would burn up and you have a lot of dust, there is a large electron depletion, an order of magnitude or possibly more. Electron density is gone because probably they are soaked up on a much heavier charge carriers, the dust. So that's the point when dust can make plasma appear non-neutral because it locks up of the dust and the mobility of the electrons that are locked onto the dust is gone. So looking ahead of Rosetta, I imagine there will be a lot of arguments about bite-outs and non-neutrality and electrons and ion density not matching. So dusty plasma waves, and I apologize to our friends who know more about waves. I didn't do justice. I only have one slide. Clearly, the non-neutrality of the plasma comes from the fact that the electrons and ions and all this charge locked up on the dust has to be neutral. So the electron and ion densities are no longer a match. So if you look at, for example, standard ion acoustic waves, and you do nothing else, just mess with the electron density and lock it on the dust, that dispersion relationship will be changed, and it will be changed to proportional to the discrepancy between the ion and the electron density. The phase velocity will be different if you have dust on the standard ion acoustic wave due to the presence of dust. This is not really a dust wave or waves in the dust medium, but it's manifestation on another known plasma wave that is changing due to the presence of dust by making the electron-ion density ratios not equal. You could also expect actually a dust acoustic wave. And the dust acoustic wave, this would be the dispersion relationship that has to do with the density of the dust and the density of the ions. So when we're going to do our field measurements and high-frequency radio, there will be a lot of excitement at Comets. I expect all these plasma waves to be very much alive. And here it is, back against from Iowa. This is a dust acoustic wave. That's the one when the distances are on human scale. And we have to be prepared if you see structures or plasma measurements that tell you very, very low frequency waves that are possibly have to do with dusty plasma waves. So I'm down to my last object or discussion, and dust in the heliosphere, interstellar dust and nanodust. This is Ulysses, 92. It went by Jupiter and took a south turn, and ever since it's in an orbit. You might recall, or you might not recall, that launch was delayed by 6 years due to a shuttle accident. And as a silver lining, by no means in any way comparable to the disaster, that 6 years was incredible because, of course, Now the encounter was such that the orbital plane, the new orbital plane, where Jupiter happened to move in 6 years, is almost perpendicular to the incoming interstellar flow. The incoming interstellar gas, and I will tell you in a second, the dust as well, is coming at right angles to the orbital plane of Ulysses. Should we have launched on time, that would not have happened. So, as the Earth moves around, this is the direction of the interstellar gas as we know it. And as Ulysses would report to you at the encounter at Jupiter, there is a beam, or so it appears, there's a beam of dust particles that coming more or less from the same direction as the interstellar gas. Hydrogen and helium flowing through the solar system. Coupled with it, dust particles are coming as well. The measurement is kind of difficult. As Ulysses goes around and around, of course, it is spinning, so the dust detector is turning. But the Ulysses high-gain antenna that is always pointing to the Earth is also doing strange things. So the rotation angle, the way that the dust impacts were recorded, is the angle of the bore side of the dust instrument from the celestial north. So you could imagine as you go around and the Earth is moving around, a spot in the sky where the interstellar dust is flowing into the solar system, in the language of rotation angle is complicated because of the Earth is moving, because the spacecraft is moving, and so forth. So as a function of time, this is in the language of rotation and angle, this is the direction of the interstellar helium flowing through the solar system. So the first observation that Ulysses made, that contrary to our friends in astrophysics, the dust size distribution is really such that we are missing a lot of small particles. Then you had to remember that Eugene Parker in 1964 and friends Eugene Levy and Randy Jokipi pointed out already that if you imagine the whole heliosphere as a big comet, and of course there's a pileup of magnetic fields and the outgoing plasma is turned around and forming the heliosphere and the incoming interstellar plasma is flowing around it, small particles are prevented to getting into the inside of the heliosphere. There's a screening. You're forced to go around with the plasma, with the interstellar flow. Small particles will not make it, so this is probably an artifact of the screening of tiny particles. And there is something else. This is the first set of data published from 92 to 2004. It's changing in time. And so it appears that there is a characteristic size that makes up most of the interstellar dust, and they are roughly about 0.3 micron in radius. The continuous line is computer simulation, and I will tell you how that works, of 0.2, 0.4, 0.3 microns, and the 0.3 microns are the ones that seems to match the data well. This is the rotation angle as a function of time. These are the fluxes showing you sort of a minima somewhere around 99. These are parts when we encounter Jupiter and the stream particles are messing up to the clear identification of what interstellar, what is interplanetary, and what is stream particles from Jupiter. So the red line is interstellar dust only that can be very well identified because they're coming at 26 kilometers per sec in from very close direction where the gas is coming from. That is actually way above the escape speed at that distance, so those particles are not from the solar system. So this is it. This is now the directionality. I think these are 6 months averages or so. And you see big deviation from the direction of the gas flow. The red was the helium or hydrogen flow, and these are the dust particles coming. And the first notice actually were for around 2000 and 2006, where Ulysses actually, I'm sorry to go back like this on you. So we are talking about exactly the same part of the orbit. And I'm looking at what happened between around 2000, 2000, and 2005. And I noticed that the general directionality of the interstellar gas is changing. It's changed almost 30 degrees. The beam appears to be shifted. Well, it's unlikely that the heliosphere shifted. Something happened to the dust inside the heliosphere, that its directionality seems to be different from one period of time than the other. And what is different, of course, is what the large-scale structure, the large-scale magnetic field is doing, how does it fills in the heliosphere. A dust particle takes about 20 years to go from 100 AU down to the orbit of Ulysses, down towards the sun. Through that period of time, in addition to gravity, in addition to radiation pressure, it feels the electrostatic force. And its orbit is winding through the heliosphere, and it is responding to the large-scale structure. And it will arrive at Ulysses at different directions at different times. So I'm sure they are very familiar with this type of a picture, what the heliosphere is forming, the current sheet, and we have a good model, or as good as it gets, how we fill out the entire heliosphere to follow dust particles, depending what the sun is doing. And this is a simulation that I will show in a sec. That's the spacecraft. This is the plane of the orbit of Ulysses. Ulysses will go around and around. And this is the stream of dust particles that are crossing the orbital plane. That's a standard F equals ma code with some sort of a model what the heliosphere is doing in all those times. See, it's complicated. Not only that the dust is shifting around, but as the spacecraft is moving on its own, it could go into low and high density regions. So the dust density I measure, I have to be mindful what the spacecraft is doing, what the dust particles is doing, what exactly I'm going to measure on Ulysses. And this is what I think Ulysses should measure. And yes, we could reproduce the minima somewhere around 99. And it really just has to do what the current sheet is doing, what the sun is doing, how the large-scale structure of the magnetic field fills out the heliosphere. And as far as directionality goes, well, maybe it's difficult to reproduce and capture all the physics. But clearly I can show you, just by the changes due to solar cycle, what the magnetic field is doing in the heliosphere. Dust particles, interstellar dust particles will do different things. All right, so now I'm really on to the last bit. Not only dust particles are coming into the solar system, dust particles appear to be flying out of the solar system. Large particles, like 100 nanometer size particles, if they are born close to the sun, they can actually be thrown out by radiation pressure. That beta value, the radiation pressure over gravity, can be larger than 1. And then you'll be pushed out. If you go towards even smaller particles, then their motion is dominated by electromagnetic forces. And I could show you how it works out, or Nicole Meyer-Werner showed us how to work out. Tiny, tiny dust particles born close to the sun can get up to drift speed that are comparable to the solar wind speed. 300-400 kilometers per second, if you are as small as 10 nanometer or so. Because the motivation for those type of speeds and size of particles was the fact that when these particles would hit the spacecraft, make a small plasma cloud that you could see in the antennas. The exact physics of all of that we are arguing since 1981 or so, when Voyager went through the ring plane of Saturn, and we noticed that yes, plasma wave and radio wave antennas can be used as proxy for dust detectors. I don't want to get into the physics of that. If you are interested, we built a whole set of experiments, and we could test these ideas at the dust accelerator half a mile from here. Here it is. This is actually stereo A, I believe. This is time of days and the flux that these things are reporting, and it is highly variable. These particles are doing strange things, and it's not obvious why the fluxes are changing as the spacecraft goes around the sun. Imagine now the same code that followed dust particles, interstellar dust coming in. I can start dust particles close to the sun and follow their motion up towards the spacecraft. And that's a simulation like that. All particles were started on circular Kepler orbit, close to the sun. And depending what the magnetic field is doing, some particles, if they are started at the right place, they will travel out with the solar wind, and by the time they get to 1 AU, they happen to be close to the ecliptic plane. Those are the ones that I could detect. The ones that are far above and way below, you would not see them. These were all started in the ecliptic plane, and there is only 3 regions that would translate into an angular distribution of intensities that would be detected by stereo. The middle panel shows the same graphics in a strange coordinate system where the ecliptic plane, or the current sheet, is shown as that line. Particles are started in the current sheet or close to the ecliptic plane near the sun. And they travel, and if they remain in the band only a couple degrees above and below, they can be detected. If you argue that the dust particles actually are not in the ecliptic plane, but they have large inclination distributions, you could still maintain a high variability. And by no means can I reproduce the measurements, what stereo A and stereo B did, or other spacecraft. But I can at least report to you that it will be variable. Even if the source at the sun, due to breakup or delivery of small particles or whatever, even if the source is steady state, by the time you measure it at the spacecraft, it will be highly variable. And that variability is a manifestation of the magnetic field structure between you and the sun. This is it. Oh, I'm so sorry. This is very faint. Stereo is the red lines. And the blue ones are, I believe, 3 and 10 nanometer size particles. By no means do I capture reality, but at least the variability and the temporal changes are obvious. I don't need a time-dependent source near the sun to have a very time-dependent measurement at 1 AU. So, I think this is almost down to my last slide. What can I do? You are in a heliospheric physics school. What can I do for the heliosphere with dust? And actually, a whole lot. Imagine that we build an instrument where a dust particle comes in, and we make an ion optic such that when it breaks up into electrons and ions upon impact, I will focus all the ions into a time-of-flight system, and I can tell you the composition, the mass of those particles. We have built devices like this. Cassini is flying a dust detector like this. And even a simple setup, for example, if you have silver, you could simply separate 107, 109, the isotopes, so I could convince you that it's not so hard to build an instrument that would give you a mass resolution pushing several hundred. I can tell you the composition, possibly even the isotopic composition of interstellar dust particles. And if I have a setup that I can measure the speed and the direction, with certainty I can tell you what is interstellar and what is not. So, using the interstellar particles flowing towards you at 1 AU, using the nanoparticles flowing from the sun towards you, you could kind of build a dust tomography, what the large-scale structure of the heliosphere is doing. It's not an obvious inversion because the particles coming from the outside travel 20 years. The particles that are traveling towards you from the inside traveled only a few days. So your job is not easy, but the better the model you have for the heliosphere, the dust measurements will be matched to a higher and higher degree. And I think that would be an incredibly useful exercise. So, this is it. As a summary, clearly, I hope I had the chance to tell you that these issues are relevant to a number of in situ and remote sensing observations. Typically, plasma measurements and wave measurements cannot be done separately without knowledge about the dust, especially in regions where the dust density is high. You have to be mindful and do this analysis talking to one another. You cannot analyze data one instrument at a time. So, I was asked to leave you with a set of problems to think about. That's my last slide. They are in increasing complexity, and if you wish, work on it or think about it. And I also left you a couple references. You could certainly send me an email if you want to have a follow-up discussion. Thank you. Okay. Okay. So let's start from the outside. I think about 1/3, that's my understanding, about 1/3 of all the dust that we measure beyond Saturn is interstellar. It's quite a bit. And so out there, of course, the comets are not so active, but we still have collisions and interstellar particles hitting Kuiper belt objects, generating dust from the Kuiper belt. And those particles will migrate towards the sun due to Poynting Robertson drag. Those are the sources that I think are dominant beyond the waterline, beyond when comets turn on. As you move closer in, of course, then these particles would have a hard time passing by Jupiter. So there is a huge step down in dust density, what I think is there, or a huge step down of that interstellar and Kuiper belt dust density passing by Jupiter. But as you come closer in than Jupiter, of course, you have the asteroid belt with collisions, and you have comets turning on. So probably asteroidal and cometary dust are the ones that generate the most dust inward of Jupiter. Those are also evolving due to pointing Robertson drag towards the sun. As they get closer and closer, they skinny down due to evaporation and sputtering and collisions as the phase space is getting smaller and smaller. And then they generate a whole lot of beta meteorites, the ones that are thrown out by radiation pressure, or these other types of nanodust particles that are ground down and are going to be entrained in the solar wind. So it's kind of a huge washing machine of incoming and outgoing dust. And of course, most of them, at least from the inner solar system, will end up in the sun. Io, okay, so I think that's an interesting question. I think it's perhaps as high-speed particles near Jupiter, that's a winner. I think the stream particles versus interstellar particles, interstellar was much higher than stream, especially because they are collimated. The Io particles have a difficult time because of the tilt of the magnetic field. That hose or that source is kind of moving up and down and spraying dust all around, so it spreads out. But I can look into it. I don't have the answer on the top of my head.
How does it affect the overall? Does it have any effect on the overall global atmospheric dynamics? Because I don't see a lot. I mean, not that I know of that. A lot of
Okay. So the answer is okay. So there are interesting issues. And the expert is Fran, who is not in the room. If I recall measurements of the composition of the plasma that you think it's from Io, far away from Io, especially inward, so inward diffusing particles, there were molecules that are short-lived. And if I take a diffusion timescale, how long would it take you to get from Io at 6 to the location when I measured you at 5 or some distance away? You would come to the conclusion that you have no right to be there. But if you cover that distance partially or all the way as a dust particle, because most of them would be trapped and not be thrown out. You have to be skinny to be thrown out from the magnetosphere. If you travel part or all that distance as a dust particle and you are a local source due to sputtering and evaporation, then you could be the source of that dust particle, those type of ions. And the details of this argument escape me. What ions Fran was talking about, probably SO2 or some other weird stuff. But so yes, dust can play a role in the chemistry. But in most cases, because I don't know much about the chemistry of a magnetosphere, for me the dust and the ejection of the dust particle as a test of your magnetospheric models is already something that is worthy of looking into. If you were to change the magnetic fields, if you were to change the plasma environment, if you would change the offset of the plasma torus, you will get a different emission pattern. So the dust measurements give you kind of a reassurance that you might be right. You have the right plasma conditions as far as reproducing the dust measurements.